Alright, in this video we're going to take a look at the topic of classifying chemical bonds. It's something we began in class, and I said I'd post on the course website for you to continue viewing. I'm going to start from the beginning. If you've already seen some of this, you can skip through to the point that you need to start at. So the topic is classifying bonds. We're going to look at three kinds of bonds. In our grade 11 chemistry course, we talk about ionic and covalent bonding. What we're going to do here is introduce two different kinds of covalent bonding, polar and non-polar covalent bonding. To begin with, let's get some definitions straight. The new way of looking at bonding depends on understanding electronegativity. This is a very important term, so make sure you can define it. It's the attraction that an atom has for the electrons that it's sharing in a chemical bond. So an atom is bonded to another atom, there's electrons in that bond between them, and electronegativity measures how strongly one atom pulls on those electrons in the chemical bond. Atoms can pull very strongly, in which case they have very high electronegativity, or they might pull very weakly on those electrons, in which case they have very low electronegativity. A bond between two atoms is said to be polar if it is between atoms that have different electronegativities. So if one atom, say hydrogen, has a lower electronegativity, say 2.1 units, and it is bonded to oxygen, which has a higher electronegativity, 3.5 units, and we're going to see where those numbers come from in just a moment. This bond is between two atoms with a difference in electronegativity. So because oxygen's value is larger than hydrogen's value, the electrons in this bond will be pulled towards the oxygen atom. And that makes the oxygen atom partially negative and the hydrogen atom partially positive. And as a result, we call the molecule a polar molecule, the bond, a polar bond. We would give a little symbol above the oxygen, a delta negative. It's a lowercase delta symbol to mean there's a partial negative charge there, and a delta positive, meaning there's a positive partial charge on the hydrogen. The atom with a greater electronegativity will pull the electrons closer to it, and electrons we know are negative, so that gives that partial negative charge. In your data booklet, you have a table of electronegativity values. In fact, this is the table that's in your booklet. Different textbooks might have slightly different values, but they should be pretty close. And you can see in this table the numbers where I just used. So hydrogen is 2.1 Paulings. This is the Pauling scale, named after a chemist who introduced this idea. And oxygen over here has a electronegativity of 3.5. Now this table is in your booklet, and during tests and on the exam you'll have access to it. But notice that there is in the table a periodic trend in electronegativity. As you go across a period, you can see that the electronegativities tend to increase. And as you go down a group like this, we can see that the electronegativities tend to decrease. Now, unlike atomic radius and first ionization energy periodic trends where you have to memorize those, this particular trend will be visible because you're going to have the data booklet in front of you during your test. Okay? But notice that the metals over on the left have the lowest electronegativities. In fact, the very lowest is down here at francium, while the non-metals over on the right tend to have the largest electronegativities, and fluorine over here has the largest. And you might be wondering, what about these noble gases? And you'll see they don't have electronegativity values assigned to them. And that's because electronegativity measures the attraction for electrons within a chemical bond. And we remember that noble gases tend not to form compounds. They don't react with very many things. So they don't tend to form bonds, therefore they don't have electronegativity values. If you have your data booklet, keep this table open because we're going to need to refer to it as we look at some other examples. We'll start with discussing ionic bonding. There are several ways to discuss it based on grade 11 chemistry. You might remember that bond between a metal and a non-metal is described as being ionic. So metals are over on the left side of the table, non-metals on the right side of the periodic table. So if you see a bond like that, you can guess it's probably an ionic bond. If it's ionic, it has cations, which are positive, attracted to anions, which are negative. The cations would have been a metal originally, and they lost their electrons, and the anions would have been a non-metal, and they gained their electrons. So there has been a transfer of electrons from the metal to the non-metal. In grade 12 chemistry, we're going to look at how to classify ionic bonding using the concept of electronegativity. So let's switch over to that. We're going to look at an ionic bond as a bond that forms between atoms that have a very large difference in electronegativity. So large that one of them attracts the shared electrons so strongly that it basically takes them from the other atom. And that's in line with the definitions we just discussed. The difference between the two atoms is going to be 1.7 units or 1.7 Paulings or greater to qualify as an ionic bond. Now, a typical test question, say a free response question, might ask you to classify a bond. So it might say, classify, and let's look at a bond between sodium and chlorine. If you were asked to classify that on a test, you'd want to show your work to get full points. So if you have your data booklet open to the table of electronegativities, take a look at sodium's value, and you'll see it's 0.9 units, 0.9 Paulings, while the chlorine value is 3.0 units, 3.0 Paulings. So you can write that down. And then underneath, you can show what the difference is. I'll use the capital delta to represent the difference between them. And you just subtract the larger minus the smaller. So in this case, 3.0 take away 0.9, the difference is 2.1 units. But we just said above that if the difference between the two atoms is 1.7 Paulings or greater, the bond would be considered ionic. So since this is 2.1 unit difference, this would be, therefore, an ionic bond. So that would be full points on a test. You showed me the two electronegativity values, you showed me the difference between them, and then you correctly classified the bond as being ionic. So let's take a look at another type of bond. In grade 11 chemistry, you learned about not only ionic bonding, but covalent bonding. And back in grade 11, you would have probably described a covalent bond. That is one that forms between two non-metal elements. There's no metal involved in the covalent bond. You probably would have thought about covalent bonding as being a sharing of electrons, as opposed to the transfer of electrons that we just talked about with ionic bonding. In fact, the very word covalent means sharing valence electrons. Using electronegativities, though, we can take that concept of sharing electrons, that concept of a covalent bond, and we can talk about two different kinds of covalent bonding, so we can be a little bit more precise. The first type is called a polar covalent bond. Okay, so in your biology class, you may have used that term polar before. You might have referred to the water molecule as being a polar molecule. Now we'll see where that comes from. So what makes a bond a polar covalent bond? This is the result of unequal sharing of electrons. So unequal sharing. So you've got an atom bonded to another atom where there's a small difference in electronegativity between them, and as a result, the electrons are shared unequally. If the difference is large, the bond will actually become ionic. If it's a smaller difference, it'll be a polar covalent bond, unequal sharing. To put some numbers on that, if the difference between the two atoms in electronegativity is 0.4 to 1.7 Paulings, so greater than 0.4, but less than 1.7 Paulings, the bond would be considered polar covalent. The graphic that I've got on the slide shows hydrogen bonded to fluorine, but I'm actually going to change that. I'm going to make that a hydrogen atom over here bonded to a chlorine atom over here, so Cl. Okay, so let's make that a hydrogen bonded to chlorine. If you are asked on a test to classify that bond, so classify the bond hydrogen bonded to fluorine, let's jump in and use our electronegativity values from your data booklet. Hydrogen's value is 2.2. Be sure you're looking at the correct table, not the periodic table, but the electronegativity table. On tests, I've seen students subtract molar masses of elements rather than their electronegativity values. It's kind of funny. The chlorine atom's electronegativity is 3.0. So the difference between those two would be 0.8, and therefore, since 0.8 is bigger than 0.4, but less than 1.7, this bond is a polar covalent bond. Polar covalent. Practically, if you had a hydrogen bonded to a chlorine, as we're trying to show in this picture, so here's a hydrogen atom, here's a chlorine atom over here. Okay? What does it mean that the bond is polar covalent? It means that the electron cloud between them is being pulled more towards the chlorine atom, away from the hydrogen atom. So now the chlorine atom in this bond becomes partially negative, while the hydrogen atom becomes partially positive. As a result, one side of the molecule is negative, while the other side of this molecule is positive. Now, because of that difference, the molecule is polar, has a pole at one end that's negative and a pole at the other side that's positive, and that creates intermolecular forces between the molecules. So another HCl molecule that's maybe sitting over here, HCl, which has a positive hydrogen and a positive and a negative chlorine, that is going to be attracted to this molecule because of the negative positive charges like that. So polar covalent bonding resulting in polar molecules is really an important concept when you look at intermolecular forces. But we'll stop there. On this test coming up, you really just have to classify the bonds. So the last type of bond, if you're thinking logically, should be straightforward. This is a non-polar covalent bond. The sharing, it's covalent, so they're sharing, and it's equal sharing. The reason it's equal sharing is because the atoms in the bond have pretty much the same electronegativity. Okay? They may not be exactly the same, but there's a very small difference between them. In fact, if that difference is 0.4 Paulings or less, the bond is considered non-polar covalent. So a good example of this, oops, I just spelled classify wrong. Okay. A good example of this would be the carbon-hydrogen bond, which is also very, very common in organic chemistry and biology. If you've got your table of electronegativities, take a look at the values. Carbon's electronegativity value is 2.5 Paulings, while hydrogen's electronegativity value is 2.2 units. And so the difference between them would be 0.3 units, and that is less than 0.4. So if it's 0.4 or less, the bond is going to be, therefore, non-polar covalent. Okay. So we've got three kinds of bonds. Ionic bonding, when the difference is 1.7 units or larger, the difference in electronegativity. A non-polar covalent bond is at the other end of the extreme, where it's 0.4 units difference or less. And if there's an in-between difference between 0.4 and 1.7, the bond was referred to as a polar covalent bond. Okay, try it, just a few examples. Show your work the way you should do on a test question to get full marks. So for lithium fluoride, LiF, we look up the values in our data booklet for electronegativity. Lithium's value is 1.0 Paulings. Fluorine's value is 4.0 Paulings. So the difference between them is 3.0 units. And that's large enough, bigger than 1.7, and therefore this would be considered an ionic bond. Bromine, if you just thought about it for a minute, you could do without even looking at a table, right? Because if you've got two atoms that are the same, the difference between them will be what? It's going to be 0. If we look up the values, 2.8, so the difference is 0, and therefore that is a non-polar covalent bond. Difference is 0.4 or less, it's non-polar. Iron oxide, we look up the values for iron and oxygen, and iron's value is 1.8 Paulings, oxygen's value is 3.5 Paulings, and so the difference here is 1.7 units. And that falls right on the border. For the sake of just knowing what to call it, it's actually right in between ionic and polar covalent, but we said that 1.7 or larger would be considered ionic, so therefore this is an ionic bond. And to be honest, there's not much of a difference in the character of the bond if the difference is 1.7 or 1.8 or 1.6, but just so that we know what to call it on a test, 1.7 or higher, and we'll call it ionic. I'm going to erase some of this just to make some room. The last two examples, probably beating this concept to death now. Aluminum chlorine. Aluminum's value is 1.5 Paulings. Chlorine's electronegativity is 3.0. So the difference between them would be 1.5 units. Since the difference is between 0.4 and 1.7, this will be, therefore, a polar covalent bond. So it's a pretty straightforward concept. Easy 2 or 3 marks on a free response question, or easy multiple choice question as well. That last example that I just realized is one we just did, so we'll leave it off here. I hope that helps. This is one of the last topics in our first unit before we move on. So good luck in preparing for your test.